Welcome to Simple Linear Regression. I'm calling this chapter 14.1 because your textbook does multiple and simple linear regression together in chapter 14, so you can just refer to the parts about simple linear regression as you're reading along. All right, so we learned analysis of variance already, ANOVA, and this allowed us to determine if there were differences in the mean of a quantitative response for different levels of a categorical predictor. So here we've got an example where we have morning, afternoon, and night shift, and size of some kind of an error on a production line. So the response variable there is quantitative, but the predictor is categorical. In simple linear regression, we're going to explore how the mean for a quantitative response changes with differing values of a quantitative explanatory variable. So it's going to be kind of like ANOVA, only with a continuous set of categories on the x-axis, if you will, a quantitative explanatory variable. Here we've got an example where we're looking at deadlift personal records as our quantitative response and bench press personal records as our quantitative predictor. But before we learn about regression, we're going to talk about something called the correlation coefficient, R. The correlation coefficient is a statistic that measures the strength and direction of a linear association between two quantitative variables. So a linear association between two quantitative variables. R goes between -1 and 1. A correlation of 0 indicates that the mean of y does not change with x. If your correlation is positive, that is greater than 0, it indicates a positive association. This means that both of the variables increase together. When above average values and below average values occur together, we call that a positive association. And what that looks like on a scatter plot is it moves upward from left to right. A correlation of less than 0, a negative correlation, indicates a negative association. The negative sign indicates that higher values of one variable are associated with lower values of the second variable. And when above average values of one variable occur with below average values of the other variable, we call that a negative association. And on a scatter plot, this looks like a downward relationship. It moves downward from left to right. All right, so if you happen to have a correlation of +1 or -1, that means that your data is in a perfect straight line, which is never going to happen in practice. Okay, but in a perfect world, if your data were in an exact straight line, you get a correlation of +1 or -1. Of course, +1 would be if you had a positive relationship, -1 would be if you have a negative relationship. And this is the formula for calculating R, but again, this is a course on the applied. We are not going to be hand calculating things. We're showing it to you just so you have it for reference and so that you'll understand its relationship to the slope in regression in a little bit. The slope formula is kind of hiding inside of this correlation coefficient formula. All right, so now let's examine these properties of the correlation coefficient. So this top left picture has a correlation of 0. Now we had to calculate that in a computer. Notice it's just like basically a scattered cloud of points. If you had to fit a line through it, it'd be hard to say that was a linear relationship. Now this next picture in the top middle has a correlation of -0.3, and that's saying if you were forced to fit a line, it should be in the negative direction. But the 0.3 being close to 0 tells you that it's not very close to a linear relationship. All right, the next picture, correlation of +0.5, means that the positive means that if you fit a line, it would be uphill. And the 0.5 being kind of halfway between 0 and 1 tells you it's not super tight to a linear relationship, but it is starting to look kind of linear. On the bottom left, we've got a correlation of -0.7. That means that the line that you would fit would be downhill. And the 0.7 being close to 1 tells you that it's tighter to a linear form. +0.9, positive means the line would be uphill. The 0.9 means it's really tight to a linear form. And -0.99, the negative sign tells you that the line would go downhill. And the 0.99 tells you that it's very, very close to a linear form. So the closer your correlation coefficient is to 0, it's probably going to look more like a cloud of points. And the closer that you get to positive and -1, it's going to be tighter and tighter to a linear form. All right, so now we're going to jump into simple linear regression. So we've determined that there is a linear relationship between our variables, and maybe we want to fit a line to the scatter plot to make predictions of the response variable y. So this is the example that we opened up with, bench press versus deadlift weights. And what I've done is I've just fit a line to that scatter plot of data. So we're going to work first with the data set that I have compiled when I was investigating the possible gas tax hike, which eventually did go through here in South Carolina. So this was data collected on gas tax revenue. The most recent revenue data that was available at the time that I made this example was 2014 data. There is 2015 data available now, but we're still going to work with the 2014 data. So I just collected a number of variables. I gathered median income for the states, number of registered vehicles, total licensed drivers, a bunch of different variables because I was trying to find a relationship to see if we could determine what was an anomaly as far as gas tax goes. All right, so what I ended up looking at was the relationship between total revenue that a state collects in a year against the number of registered vehicles, and it's quite surprisingly a pretty good linear relationship. All right, so this is the scatter plot of the data of our thing we're trying to predict, which is total gas tax revenue, against the thing we're using to predict it, number of registered vehicles for a state. And you see this one way out here. Can you guys guess which one that is? Yep, it's California. Okay, so we'd like to fit a straight line to this data. Why linear? Well, quite simply because it's the easiest to use and interpret. In regression, we're going to always want to fit the model that's the simplest to use and interpret. And does it look like fitting a straight line seems reasonable here? Sure. The scatter plot looks pretty linear to me, so why not? We'll go ahead and try to fit a line. So let's review the equation of a line. The simple linear model relating y and x is y equals b naught plus b1x. And I'd be willing to bet if you went to K-12 school here in the States that you probably learned the equation of a line was y equals mx plus b, where m was your slope and b was your intercept. Well, in regression, we call the intercept b naught, and we're going to call the slope b1. So it's just a different naming convention for the same line that you already have learned in the past. Now let's investigate what these mean. Okay, the slope and the intercept are two different things. So the slope, the intercept, b naught, is the point where the line crosses the y-axis. So if you put in 0 for x, the point where the line crosses the y-axis right here is b naught, your intercept. And b1 is the slope, and that's the one we're going to be concerned with. This is the change in the y over the change in the x, which you may have heard before as the rise over the run. Okay, so the slope tells you if you go so many units to the right in the x direction, how far up or down do you go in the y direction? Now we're always going to talk about the slope in relation to the x's increasing by 1, and we'll do an example of that, and you'll have plenty of examples of that in your homework and practice homework. Okay, so the linear regression model of y on x assumes that y is the mean of the y's given the x plus some error, where this conditional mean is linear with the conditional mean equaling beta naught plus beta 1x. What is that? That would be if we had the population scatter plot of all the x's and y's. That would be the population line that fit through that relationship. And we're going to assume that the average of the errors is 0 and that the standard deviation of the errors is sigma of y given x. We're going to use b naught to estimate beta naught, b1 to estimate beta 1, and we're going to use s of y given x to estimate sigma of y given x. So we're going to use our sample estimates to estimate these population parameters. And then we can estimate or predict the mean y at a given x so that the estimated mean of the y's at that given x is b naught plus b1x. And this b naught plus b1x is the line that we're going to fit to the scatter plot of data. All right, so now we need to talk about which line. So suppose this was my scatter plot of data and I wanted to fit a line to it. Well, I could fit a line to it. And I think we all agree that line doesn't fit very well, but just humor me for a moment. How can we measure the fit of this line to this data? Well, one idea is to look at something called a residual. A residual is the vertical distance up or down to the line from a point y. It's the observed y minus y hat, the predicted y. So the observed y is the yellow dots here, and the predicted y's are all on the blue line. Okay, so that's the residual. And a positive residual is going to happen if your point is above the line, and your residual is going to be negative if a point is below the line. All right, so one idea that we have is to measure the offness, how well it fits, by just looking at these residuals and taking an average. But that turns out to be a bad idea because the negatives and positives can cancel each other out and make your sum of your residuals 0 even for a very bad line. So another idea is to go ahead and square the residuals. We can actually take the square, which we can picture here just like this, and that's a pretty good idea because that way we don't have the negatives and positives canceling each other out. But now you can see how this line is missing some of the points big time because we've got some really big squares. So we need to talk about which line to fit. How are we going to figure out which one is the best? Well, let's try this one and look at the sum of squares. And we can already see that this one's cutting through the points more equally everywhere, right? So the name of the game that we're going to do is we're going to try to minimize that sum of squares. And it turns out that this formula, this set of formulas, minimizes that total sum of squares. So we call this least squares regression. Now you're going to always use R to calculate these coefficients, this B0 and B1. So don't worry about the formulas too much. We do want you to notice that this formula for B1 is kind of hiding inside that formula for the correlation coefficient. They are very related to each other. Since the correlation coefficient is describing the strength and direction of a linear relationship, and this is the slope of the line that we actually fit through that scatter plot of data. Okay, so now we're going back to our data set. And what we've done is we have fit a line to our gas tax revenue data. But this is a little bit unwieldy because look at the units. The Y is in total revenue in thousands. So for California, we're a little bit above 6 million thousands, which is kind of hard for me to wrap my brain around. And the numbers on the x-axis are all really big, right? So we're going to talk about something called ill-conditioned data. Unusually large or small data is called ill-conditioned. This can lead to a loss of regression accuracy from rounding, or awkward estimates with scientific notation and awkward interpretations. So try putting your data on the same scale or similar scales or a scale that is not unwieldy. So what I've done is I've rescaled everything to make revenue in billions and registered vehicles in millions. And I think that looks a lot better.